Okay, so we're drawing an energy level diagram for an endothermic reaction. So for an endothermic one, I need to have my reactants have a lower amount of energy than my products. So I end up with a curve that looks like something like that. And then if I'm going to label this thing, I'll do, this is energy, and this could be time. This is reactants, products. From here to here is your delta G. And then from there to there is your activation energy. And there's your transition state.
I have a question about that. I thought your activation energy was like from your products to your transition state.
Nope, from the reactants. It's the amount of energy needed to go from what I start with to get the reaction to actually happen. Yeah, from that point to that point isn't anything. Any questions about that one?
Would that be like an example of a cell phone?
Charging, yeah. All right. So, which trials would you like to pick? So if I pick trial 1 and 2, I have this goes up by 0.5. We okay with that? It goes up by a half. What I mean by, it goes up by 50%. We okay with that? So if I multiplied 2 by 1.5, it would be 3, right? So how much do I need to multiply this number to get it to that number? So they went up by the same amount, correct? So then what order is it for A? All right, so it's first order with respect to A. B, looks like maybe I did this not quite well enough. So this goes up by a factor of 3, right? So we have 3 is equal to, and then what's the change here?
It's like 10.
We'll say 10. So what number needs to go there? 3?
Is it only ever whole numbers? That's what I was thinking. Yeah, sorry, Rob, this was
It's okay.
way out of my league.
It's not an issue, it's just that what I had been giving you in these examples was everything was nice and clean. Okay, so what is this close to? 2? So I'd go with a 2. How would you verify this? Because 3 times 3 is what?
Or 3 times 3 is 9.
Okay. So we're close to 10. So how would you check to see if that number was really 2? If this was you in response to this experiment? I would do more trials. Does that make sense? You guys did 7 trials on Tuesday. You did 7 trials because it's humans and they're gonna make errors and you're gonna be like talking to each other and then somebody's gonna look down and be like, oh, when did that turn purple? There's no way that didn't happen on Tuesday. It happens every lab. Like, did it happen 2 seconds ago or was it 9 seconds ago? Because that'll make a difference. So you would just do this several times. So the chances of you hitting a number that gives you 1.5 and 1.5 in the lab is pretty slim. But 10, right? Pretty close to end up being 2 because the 3 times 3. So we'll run it as it's 2. So then I have my my first order and my second order, and then I need to solve for the rate constant. So what I have is rate is equal to K, A to the first, B to the second. So I'd rearrange that and say that K is equal to rate divided by A and B squared. And then I would just throw numbers in. So 0.26 times 10 to the negative 9th divided by 0.002 and 0.0075 squared. Are we okay with that?
You need to know
Took rate 1 and you took times and tens.
Ooh. You're right, I need another 0 right there. For this one? Nope, no. I'm sorry, what'd you say, Christine?
That you just took the rate and just are dividing it out by initial A and initial B to check it, just to see if you end up with.
Yep, just so I know what my constant is. What happened to the times 10 to the stuff? I just changed the into decimal format, right? So I got a rate constant that's equal to 2.31. So it looks like I have 2 sig figs. So when I'm going to write my rate law, I'd write rate is equal to 2.3 a to the first, b to the second. So that right there would be the answer.
So when I did that, I got 0.23, but I don't know.
No, looks like I got a decimal place in the wrong spot. There we go. I'll erase that, and I'll put a dot right there, and a dot right there. So 0.23.
Okay.
So it doesn't matter which ones you pick?
Totally doesn't. You should get about 0.23 no matter which one of the trials you pick, if not exactly 0.23.
And we don't have to worry about units on that yet, on the guess.
The units get crazy because of the exponents, so I don't even, it doesn't matter.
Okay.
How about this one? What was the trickiness in this one?
The exponent.
Yeah, the exponent here is a 1, right? So this doesn't go down, it goes up. So this is actually 35 times 10 to the negative second. Or you can just take all these numbers and write 0.043, 0.086, or 0.350. Oh. Let me try that again. 0.043, 0.086, and 0.35. So then it's obvious to go up. Okay, which trials are you picking?
1 and 3.
1 and 3? Okay, so for 1 and 3, x doesn't change. Y goes up by 2, factor of 2. So 2 is equal to what? What do I got going on over here? From there to there. 8?
8.1 or something like that.
That sounds good. So then it's third, right? Third order with respect to y. And then for my other reactants, I've got 1 to 2, and so this goes up by 2, and this goes up by 2, so it's first order with respect to x. So then I'll have, say, 4.3 times 10 to the negative second divided by 0.0014 times 0.08 cubed. Divided by 0.0014 divided by 0.08 cubed. Whoa, that's huge. So 6. How many sigs do I have? 6.0 times 10 to the 4th. So then I'd have my rate is equal to 6.0 times 10 to the 4th x y cubed.
As far as like what determining what you're asking, when you want us to write it with the number that we found, that's the rate, that would be the rate law.
Yeah.
Okay, and then the rate constant is just, and then the order.
You can't write the rate law without knowing the laws, without knowing the orders. Yeah. When you write the rate law, you need to include like the 3 right here and the 1 right there, so then I'm assuming that you're already gonna calculate out what the, well, yeah, you couldn't get the K without knowing what the orders are.
So finding the order is just part of it.
Yeah, that's the, you see one of these, just do that first.
Okay.
Questions about those?
I'm confused about how you got Y, like the order for the Y.
Did we say it went up by 8? We got 0.35 divided by 0.043. Yeah, so that goes up by about 8. So if
You're using the numbers underneath the box there?
I'm using the same number.
Okay.
So if I'm going from this value to that value, the change here is about 8.
Okay.
So then how do I get an 8 change out of a doubling? And then I'd have to cube 2 to get to 8. Calculate label draw voltage cell for zinc and magnesium. Okay. MG. Zinc. And it doesn't really matter, kind of magnesium, anything, say chloride. And we'll say zinc chloride,
As long as it's a soluble.
as long as it's a soluble substance that, yeah, exactly. All right, and then I'll just put NaCl in there because it doesn't really matter what that solution is. And which direction are the electrons running?
So this is
They're running to the zinc or from the zinc? So the only way to know that is to look at a table like this. And so I've got magnesium and then zinc. So magnesium is the 5th one down, zinc's the 7th one down, so magnesium's higher, so magnesium's more active, so magnesium will be transferring electrons to the zinc. So I've got magnesium sending electrons to my zinc. And the half reactions for this are going to be zinc ion plus 2 electrons is turning into zinc solid. And the other half reaction is going to be magnesium solid turning into magnesium metal, aqueous, plus 2 electrons. So those work out for us, that it's 2 and 2. If I'm going to draw the half cell or the overall cell notation for this, just so I can write it down, it'd be magnesium solid turning into magnesium ion, salt bridge, and zinc aqueous turning into zinc solid. And then to calculate the voltage of the cell, we're going to need to look that up. And so if I go over here, I see that the magnesium is written backwards, right? And so it's actually generating 2.38 volts. And the zinc is written correctly. So that's 0.76. So I've got
So there's 3.1.
and so what do we get there? 2 and 8, 13. Yep. 1.62 volts. Would this make a good battery? It would make a good battery, right? Those are 2 metals that are not that expensive. Neither one of them is exceedingly heavy, and it generates a voltage of more than 1.5, so it could be used as a AA or a AAA or a D or whatever normal battery time.
When when you take the two half, okay, so say like, the example we talked about the other day, the charges didn't equal, like, one carried a plus, or, yeah, whatever, two, one carried one.
We had silver and copper.
Yeah.
And the silver would only be one.
Right.
So to get these things, these half reactions to cancel out with each other so you can add them up correctly,
Yeah.
you have to have the same number of electrons on one side of the arrow for one reaction as you have on the other side of the arrow for another reaction. So in this reaction, I've got two reactions on the left side of the arrow, and I've got two electrons on the right side of the arrow. So then I can just add them up and be done with it.
Just
But
one time each.
right, just once each. But if this magnesium was in one electron, I'd have to double everything in there so I could cancel the electrons out. And then in the math, I would have to do the magnesium twice
Double the magnesium to compensate so that it's balanced with the zinc.
with the electrons.
Right.
Yeah.